Okay, let's have a look at this then. So I think we've exhausted everything that we can do on this sheet. Boys, can I have a bit of quiet, please? I think we've exhausted everything that we can do on this sheet at the moment. Now, if you have a look at question 5, A and B, it's starting to talk about transformations, which we can do with matrices, okay? So I hope you saw on like last Friday, we looked at this sheet, okay? We looked at this sheet here, which was effectively utilizing matrices and multiplication of matrices to get some particular result out, okay? So matrices are really useful if we want to work with tables of numbers. I'm now going to show you another application of what we can do with matrices. And it's this idea of transforming matrices. So we can use this idea of taking some particular shape and being able to transform it, okay? So the way which I want you to understand this is by, first of all, drawing yourself a coordinate grid. Okay, so it's just a regular coordinate grid, because I think that's the best way to start. Now, by the way, we're only going to look at two-dimensional transformations, in other words, left and right and up and down. You can also apply this to forwards and backwards as well, okay? So in other words, 3 dimensions, but we're only going to look at 2 just for the sake of simplicity, okay? All right, now the way which we're going to understand this is by, first of all, considering what's known as our basis vectors. Okay, now you don't need to know the name basis vectors, but I think it's useful because it means that we can talk about this more accurately, okay? And just to kind of say this explicitly, I'm going to mark on x and y on my diagram. Now what a basis vector is it's the equivalent of I and j when we were looking at vectors. Can anybody remember what was I and what was j?
I was right, step to right.
Good. How many steps, sorry? Just one, wasn't it? Yeah, so I was 1 step to the right. In other words, I was what vector? Can you give it to me as a column? 1, 0, right?
Yeah.
I was 1, 0. What would j be?
0, 1.
0, 1, okay. These would be known as our basis vectors. Now, it's a basis because that's the starting point, yeah? If you remember, you could get to any point on this coordinate grid just by thinking about it as steps to the left and steps up, okay? So multiples of I and multiples of j. So in fact, I'm going to draw I and j on my grid. So here is I, okay? I'm going to draw him in, and I'm going to draw him in blue. That's I, 1 step to the right. And I'm going to draw j in. So here's j, 1 step up. Is that okay? So I've just drawn him in. Okay. Now, if I want to put this into a matrix, the way which this works is like this. So I'm going to draw myself a matrix. It's going to be a 2 by 2 matrix because I'm working in 2 dimensions. Okay. And when I put a coordinate into my matrix, I write them as columns. Okay. So I literally just pick up I and I put him first. So I is 1, 0. Okay. So I put him as a column there. I'm just going to label him there, just to put a bit of context in there. And j, I'm going to put here. Okay, so j I'm going to put here. Do you see that? So if you like, this is a coordinate matrix, right? Now I said I'm going to introduce a few more interesting matrices. So we've just introduced square matrix. This is another interesting matrix. Does anybody know the name of it? Has anybody seen this before? Not quite there yet. Begins with an I. Not quite inverse, we'll get there. It's the identity matrix. Okay. Now can anybody think, why should it be called the identity matrix? What does identity mean? Bit more than that though, because if I swap these zeros around, so I put a 1 there and a 1 there and a 0 there and a 0 there, it wouldn't be the identity matrix anymore. So what is the identity matrix?
Only one value for one term.
It's a bit more than that, okay? What does the word identity actually mean?
Something, one, like...
It's the same. Yeah, exactly. You get the same thing, okay? That's what identical means. It's the same. So if I take a matrix then, let's take 1, 0, 0, 1, and I multiply by another matrix, let's say 3, 4, 8, 2, okay, 3, 4, 8, 2. If I multiply those two things together, what do I get? In fact, can you do that? Spend 30 seconds and have a go at that. What do you get if you multiply these two matrices together? So I get 1 times 3 plus 0 times 4. So I get 3 here, okay? And then this element here would be first row, second column. First row, second column. So 1 times 8 plus 0 times 2 is 8. This element here would be second row, first column. Second row, first column. 0 times 3 plus 1 times 4 is 4. And then this element here would be second row, second column. Second row, second column. So 0 times 8 plus 1 times 2 is 2. Can you see that when I multiply any matrix by this, the identity matrix, I get the identical thing back. I get the same thing back, okay? So the reason why it's called the identity matrix is because multiplying by it doesn't change anything, okay? I just get the same thing back. Now this is a bit like, if you like, multiplying by 1 with real numbers. If I take a number, say 7, and I multiply by 1, what's that equal to? 7, right? So multiplying by the identity matrix is a bit like multiplying by 1 in real numbers, okay? Now why is this useful? Why is this useful? How can we use this with transformations and things? Well, I want you to have a look on the screen here. What I have got is a square. So I've drawn a square here, right? So I've drawn a square on the screen, and the coordinates of the square are 1, 1, 1, 2, 2, 2, and 2, 1, okay? So 2, 2, yeah, these 4 points here. So you can see that square. Can everybody see that? Yeah? Okay. I've also put my basis vectors on. So I've put I and I've put j. Put I and I've put j. Now what I want to do is see what happens if I move I and j around. What happens to this shape here? That's all I want to do. Okay. So first of all, what I'm going to do is write my coordinate matrix. So at the moment, I've got an identity matrix here. I'm going to write myself a coordinate matrix out. So the coordinates will be like this. So in fact, you can see here, I've called them L, M, N, and K. Okay, so I'm going to write this as L, M, N, and K. Okay, this is my coordinate matrix. Remember, coordinates we write as columns. So the coordinates of L would be 1, 1. Okay, so I'm going to put a 1, 1 there. Okay. The coordinates of M would be 2, 1. So I'm going to go 2 and a 1 there. Okay, you see that? I'm just writing coordinates as columns. Coordinates of N would be 2, 2. And the coordinates of K would be 1, 2. Okay, 1, 2. So you can see here what I've got is almost like a coordinate matrix, okay? It's like each column is a separate coordinate, right? Now clearly, if I multiply by the identity matrix, I should just get the same thing back. The question is then, what happens if I move I and j around, okay? So at the moment, I and j, so I is the first column and j is the second column. Let me keep that consistent. Okay. So I is 1, 0, and j is 0, 1. Okay. My question is, what happens if I start playing around with I and j? Okay, so watch this. What I'm going to do is I'm going to pick up I, which is currently at this position here, and I'm just going to move him to there. So I'm just going to pull him outwards by 2. So watch what happens. Do you see that? The whole thing. Sorry? Kind of. What I've literally done is I've picked up the entire plane and pulled it that way by 2. Okay? My question is then, what happens to L, M, N, and K? Like, that's the question. So would you be happy that J hasn't moved. J is still at 0, 1, okay? But I has moved. It's moved to 2, 0. It's moved to 2, 0. So I'm going to move him to 2, 0. Now, could you multiply these two matrices together for me? Okay, so I'm going to give you a couple of minutes. Could you multiply these two matrices together for me? Have we done it? Okay, so what do we get if we multiply this matrix by this? Okay, so we do this multiplied by this. What do we get? So we get 2 times 1 plus 0 times 1, which is 2. Okay, this element would be 4. This element would be 4. This element would be 2. What would this element be? 1. What would this element be?
1.
This element? And this element? 2. Right? Okay. That's interesting. So basically, all I've asked you to do at the moment is multiply this matrix and this matrix together. Okay? And I get this one. Now bring it back to the diagram. Bring it back to this thing. Bring it back to this thing. I said that L was 1, 1. Where does L end up after I pull I and move him 2 steps in that direction? So he's now 2 steps away from the origin instead of 1. Where does L end up? He ends up at 2, 1, right? He ends up at 2, 1. So that's new L. I'm going to signify that by putting L dash. So that was old L. This is new L. Okay. Where does M end up? He was at 2, 1. He was at 2, 1, so he was there. Where does he end up after I've stretched the entire thing that way by 2? He ends up there, right? At 4, 1. He ends up at 4, 1. So that's new M. Okay. Where does N end up? So N was at 2, 2. N was up here. After you stretch the entire thing by 2 in that direction, where does N end up? What's the coordinates of N? 4, 2, right? 4, 2. Okay. So that's new N. And K was at 1, 2. K was at 1, 2. What happens to K after I pick up I and pull him by that way by 2? Where does K end up? Sorry, yeah, where does K end up? He ends up there, right? At 2, 2, which is 2, 2 there. Okay. Okay. Do you kind of see what's going on there? So literally, I start off with my coordinate matrix, and then this is my transformation matrix. It's basically asking the question, well, after I do my transformation, where does I and J end up? Okay, so in this case, my transformation, in fact, let me do it again. My transformation was picking up I, which was at 1, 0, and just stretching him that way by 2. But J was staying exactly where it was. Okay, and you can see that the entire coordinate grid has effectively been pulled that way by 2. Do you see that? But it's not being pulled vertically at all. So if you like, the way which I would describe this transformation is as a stretch parallel to the x-axis by a scale factor of 2. Okay? This is the transformation matrix. And the way which I work out where the new shape will end up is by multiplying my old coordinate matrix by my new transformation matrix. Okay? That's my new coordinate matrix. So effectively, I can work out transformations. I can see where they're going to go by thinking about I and J. I'm saying, after I've applied my transformation, where does I and J end up? And then I just multiply that transformation matrix by whatever my coordinate matrix is. That will be my new coordinates. Is that okay? Kind of?
We will have something like that later?
Possibly. I mean, I did it for illustration purposes in terms of this, so with the coordinate matrix. More likely, I will give you something like this, and I'll say, what transformation has happened here? So all you need to think about is, well, this was where I and J started. This is the new one. What's happened? Oh, look, it's only I that's changed, and it's basically been pulled 2 steps to the right. So it's a stretch in that direction by 2. We'll do some more practice with this. Yeah, J hasn't moved.
Same, yeah.
J hasn't moved. Okay, so J is still the same height. So it's not moved anyway in that direction. But I have moved by 2 in that direction because I was here and it's been pulled to here. Do you kind of see that? We'll do more practice with this. I want to take a break though.